all down at the top. Somebody could pull this up if they have it, please, in the e-text. Okay, so we're reviewing for chapter 21. We're going to do some of the problem set questions. Could you open that window? Anyone have 86 written down? I have a book right here, if not. No one has it written down? You have it, Matei? Oh, I got the book at this point now. You have it?
776 page.
7 what?
776.
Thank you. All right, here we go. So it says, yeah. It says, this is number 86 on page 777. Find the equivalent resistance between points A and B in the figure shown. So we've got a figure here, and it looks a little bit complicated at first. This is fine. This is a great example of something you will definitely have to do on the test. This is from chapter 21, section 2. This is looking at series and resistance together in network. So we've got, let's see, oops. We've got a starting point at A. This then goes like this. It goes through here. There's a branching off. Another branching off. Comes down, comes back in at B. I've got 2 here. Use this guy, make this a little bit better. All right, so it looks like we've got several resistances written down. I'm going to use arbitrary numbers for now, okay? So if you did this already for your notes, for your own self, that's good. I'm going to use random, because these are all decimals, and it's going to take us forever if I use these. So 2, 5, 7, 1, 4, and 3. So if you're still doing the problem set, if you're checking your work, I'm using new numbers for this example. So the question says, find the overall resistance of this network between points A and B. And this is given as point A, and this is given as point B. So we have to start by looking at this as a mix-up of a lot going on. Okay, we've got what looks like here, 2 resistors to start. Whoops. 2 resistors to start here that are in parallel. It's the leg, come on. Right there. See those 2, the 2 and the 5. We've got 7, 1, and 4 all in parallel also. We're going to replace these with 1 resistor as an equivalent here. We have to think about the branching off of all of these parts. So if you go about solving this, you look first for anything in series. Anything that's in series here should be simplified. Is anything in series? Right now, is anything in series? Nothing's in series right now, unfortunately.
Well, can't you just make that parallel circuit?
Well, but we're going to get to that, and then we'll have something. But right now, do you see anything in series? No. So, Jake, what do? Go to the...
You can put a parallel circuit into its own series.
Exactly. Make this 1 resistor, and then it will be in series with this resistor right here. And then the result of these 2 will be in network with these 2 in parallel. So let's start with 714. What is the rule that we use for resistors in parallel? In parallel. Jake, go ahead.
1 over RT equals 1 over 7 plus 1 over...
In this case, 1 over 1 plus?
1 over 1 plus 1 over 12.
Good. So it's simply 1 over the equivalent resistance in parallel equals 1 over all of the resistors in parallel. It's a sum law, but it's called a reciprocal sum. This is what you learned about when you listened to the video 21.2. So each of these resistors that are in parallel in this little mini network right here, see this big branching off? Those can be simplified using this rule. What does that give me as a decimal? Remember, I told you, do not do this with a common denominator. It's going to take you too long. You have calculators, use them. 1/7 plus 1 plus 1/4. What does that become? Give me the decimal answer for that. That didn't help much. 1.4? Okay, now, what do I want, though? I want RP. Where's RP? Is it in the numerator? No, it's in the denominator, so what do I have to do? Switch 1.4 and RP. Okay, or simply just do the inverse of 1.4. Now, this is something that you need to stick in your head or get stuck in your head. When you simplify a parallel network, if you don't know this, write it down. When you simplify a parallel network, the equivalent resistance goes down. You started with 1, 7, and 4, didn't you? And yet the equivalent resistor we're going to replace that with is 0.7. Isn't this less than all three of these? 0.7, what I'm seeing here, is absolutely less than all three of these. That always happens in parallel. In parallel. That always happens. Will? Yeah. So we start by rewriting this circuit the same way, but instead of having those three resistors, we replace them with one resistor. The rest is identical. This 2 is still here. This 5 is still here. But now we just put one resistor over here instead. That one resistor has a resistance of 0.7 now. So I'm going to circle it in pink to show you the resistor that we just replaced. So this resistor is the equivalent of those three in parallel. That's why we call it the equivalent resistance. It's replacing it. Okay, it's like saying, this is the same thing. You know what? We don't have any more of those in stock. Take this. This works just as good. It's a repair or replacement part. Same thing. You're replacing this one resistor for all three of those that were there. Now, the next step, as Jake picked up on, is look, and always, is look for series. Look for series. Ernest, where do you see series here? Sorry.
So 0.7 and 3.
Yeah, the 0.7 and the 3 are in series now. The way you can see that is there's no branching that occurs after the 0.7 up until the 3. Look from the 0.7 on. These continue one after the other. So replace these two with one resistor.
What is reverse? I did that, but it's just, couldn't you also have done parallel for like 1 over 3, 1 over 5?
No, because you always reduce series first. That was part of the thing we talked about. So in this case, oops, I thought that was the pointer. These two are in series, and then these two in series are in parallel with these two. So you have to go with first putting 2, 5 again, and then out here simply put 3.7. Why am I doing 3.7? Because you add them up. So again, when things are in series, the rule in series is that we add them together. Well, to me, it looks like right now, these two are in series. So I've got 0.7 over here. I've got a 3 over here. I'm going to put them in for R1 and R2. 3 plus 0.7 is simply 3.7. Now, last but not least, we see that the 3 that are left over are in parallel. So these 3 that are left here now, we can look at these 3 in parallel at the bottom. So we go back to our parallel law. 1 over parallel equals 1 over R1 plus 1 over R2 plus 1 over R3, as many as there are. And then we solve for RP. Again, use your calculator. Who cares about 1 over 3.7? You're not going to find a common denominator for something like that. Okay? Tell me what you get as a decimal and then do the inverse of that. What does your decimal become for that?
0.97.
Point what?
0.97.
And then do the inverse of that. 1 over 0.97?
But that's the...
That's the answer?
Yeah.
So what was the actual number before that?
1.033.
1.033?
Yeah.
He said he got 1.033 for this one.
I got 0.97.
That's the inverse.
John, what'd you get for this?
Oh,
Question?
there's a
Yeah.
question. So basically,
Check these numbers, other people. Check these numbers.
essentially, like the key to the problem is being able to break it up when you have a complicated circuit into smaller pieces.
Yeah, exactly. You need to partition the circuit. And now think about this as, all right, you know what? We've replaced these 3 resistors with one equivalent resistance. Whatever this number is here in that box is going to be our final answer. Because we're taking these 3 and just squishing them together using the parallel rule. These were in series, so we used the series rule to squish these two together to become one.
Okay.
Jake.
On a test, would you like would you use in words? Like if you asked us a problem.
I would give you the diagram if it was one that you had to consider reducing, yes. Unless I said something like anything in words might be like, there's 3 resistors in parallel. Well, there's only one way to draw that. But I'm not going to be like, the flow leaves, there's a parallel with 3, you can't describe this in words. You have to have a diagram. Unless it's something simple, like you have 5 resistors in series. Anybody can draw me 5 resistors in series, right? So it would have to be very simple for it to be given in words.
It's like the opposite.
The opposite?
Yeah.
Okay, that's fine. Just switch these numbers, please.
Yeah.
Okay, so we got 0.97 and 1.033.
Just 1.03.
1.03. So the overall resistance of this entire network is 1.03 ohms. You go from all these resistors in this crazy setup to a simplified version with only 1 ohm as the overall resistance of this network. Good question. Who was that? Ryan? 86? That was you? Mateo, you're up next, then Ernest. Mateo, Ernest.
So this one's a cost one.
Okay.
Number 100.
Same one?
Yeah.
Nice. Number 100. All right, it says, how much does it cost to operate a 120 watt light bulb for 25 minutes if electricity costs 0.86 per hour? So 8.6 cents per kilowatt hour, rather, per kilowatt hour. So let's write down our givens right away. It says the bulb is 120 watts. What is 120 watts? That's power. We're also told that its time is 25 minutes. And finally, we're told that the rate of cost is going to be 0.086 per kilowatt hour. That's what we're given in this problem right here. We're given those three things. Hey, by the way, this is an easier version of what you're going to see on the test. The reason I'll tell you that right now, in the test, I can expect you're going to have to calculate power first. And then using the power you get as an answer, do this cost analysis. So remember that you could start this problem with something like this. Put on a side note, please. You could start the problem by me giving you current and voltage. And you calculate power to start. Just multiply them. You get the power. This problem, number 100, gives you the power to start. I might give you the voltage and the current. You multiply those, you get the power, put that number in there, and then do the rest of the problem. Or maybe instead, I'll give you the current and the resistance. And that's when you use the second formula to find the power. Or what was the third formula to find the power? What was the third one?
P equals I squared over R.
Close. V squared over R. So if you're given the voltage and the resistance, you can calculate the power. Hey, so which of these three are you going to use tomorrow, do you think? Which of them do you think you're going to use tomorrow, these three, to calculate power?
P equals IV.
Yeah?
First.
Thank you. It depends on what's given, right? How do you know? You can't know. That's what I'm getting at. There's no way you can figure out right now today that you're going to use the first one. It was a trick question. Yeah. Any of the three. Maybe all three, maybe one of them, obviously, at least one of them, depending upon what you're given. Now, once you calculate the power, you'll write that down. This problem gave you the power, so I'm not actually going through that process right now. But recognize that you probably, I'm giving you a hint, will have to calculate the power and then use the power to calculate the cost. Let's go ahead and calculate that cost. Now, first, the formula for cost that we talked about was energy used times the rate that the energy costs. How much energy do you use, and what's the rate that costs per energy? Well, you're given the rate. It's right here. 0.086 per kilowatt hour. That's the rate. But what I'm noticing is that I don't like my units right now. I see a lot of units that disagree. Where do you see some disagreeing units in this problem? Let's start with one of them.
Kilowatt and watt.
Yeah, kilowatt and watt. How would I change that? Somebody else. How would I change that from watt to kilowatt?
Kilo is 10 to the third.
Good.
So we put it like 120 over 1,000, or 120 times 10 to the third.
120 over 1,000, yeah. Or just move the decimal how many spots then? 3 spots. So let's rewrite this as 0.120 kilowatts. That's the wattage we're going to use now, or the power we're going to use right there. Good. Second, where's my other unit that disagrees? Jake?
Minutes out.
Minutes and hours. What's 25 minutes?
0.416
0.416 hours. Where did you get that?
I just divided
Yeah, by 60. There's 60 minutes in an hour, right? We divide by 60 to see how many hours there are. So you could do that, or honestly, you could also just do this. Leave it as a fraction if you want, because you're going to have to deal with a decimal. What did you say, 416?
Yeah.
And 6 repeats, I assume, or is it?
Yeah, it repeats.
So as long as you give a couple decimals, that's fine. But if not, just leave it as a fraction. That works too. 25/60ths of an hour. You can reduce that, obviously, by dividing by 5. It's 5/12ths of an hour. Okay, 5/12ths of an hour. So here's the problem, though. What I'm noticing is that I don't have a formula for energy here. I don't know what the energy actually is. But earlier in the year, that's why I left a little space in that little box on the right, I defined power as energy over time. The definition of mechanical power, electrical power, mechanical power, same thing. The definition of mechanical power is the rate at which work is done, or the rate at which energy is transferred, E over T. So if I want energy, which is E, how do I get capital E by itself here? In this formula on the right, how do I solve for capital E? What do I do? Amaya? Yeah, multiply by time. So solve this formula for capital E. It tells me that energy is just power times time. So this formula here is really just power times time times rate. And the rate is the cost. The cost, okay? The rate is right here. Your units make sense now. Take a look. We got power first, 0.120 kilowatts, times time, which is 5/12 of an hour, times the rate, which is $0.086 per kilowatt hour. Why do the units make sense now? Who can explain what I'm saying? What am I getting at? Ernest, what am I getting at?
You're trying to cancel all the randomness you get dollars.
Exactly. Cost is in dollars or cents, right? Some monetary unit. Kilowatt times hour cancels with the denominator of kilowatt hour. So we can see here clearly that, again, these two units cancel with these two units right here, leaving dollars behind. What do I get for the cost to run this appliance? 0.120 times 5/12 times point, it's going to be very small, right? Times 0.086. Give me like 3 or 4 decimals.
0.0004.
So less than a penny. 0.01 would be a penny. Again, right here where I'm pointing, 0.01 would be a penny. This is less than a penny. It's about half of a penny. Okay, what were we running in this case? What was it? A light bulb, yeah. So a light bulb for a half an hour at very cheap electricity. This is very cheap. 8 cents. Look, right here. 8 cents per kilowatt hour. You don't pay that in the city. In the city, the average is like 25 cents a kilowatt hour. Some areas you pay even more. You're paying up to like 31 cents per kilowatt hour. Some parts of the country are paying up to like 40 cents per kilowatt hour. This is 8 cents per kilowatt hour. So although I said this is a half a penny, try to really multiply that by about 4. That's what you pay for in the city, maybe 3. So you're paying like a penny and a half to run a bulb for half an hour, just to turn a light on for half an hour. You're paying 1.5 cents. That's one bulb, guys. One bulb. A lamp fixture uses usually like 3 or 4 bulbs. So think about that. Now half an hour you're paying, a couple cents. Well, instead of half an hour, you leave it on for the weekend. That's suddenly 72 hours, right? Everything changes dramatically. You multiply that by 144. You're going to pay a lot more money suddenly. You're going to pay a couple dollars if you leave a lamp on for the weekend. Okay? And I think I did an example of that in section 21.3 when you guys were watching that video with Anthony that day. The example was about leaving on a fixture of a lamp with 5 bulbs or 3 bulbs or something. Okay, the same concept applies. This is literally the only way this problem can be asked. So if you don't practice this problem tonight, or practice the one that we did in class, or something of this sense, it's really on you. There's no way this can be asked differently. Laura, go ahead.
So if you have like a lamp, but like you didn't put a bulb in it and just a lamp, then you had to switch like on when it was plugged in and everything.
Is it going to draw energy?
Is that like this thing like?
It is, but it's not going to draw as much power as it would if the bulb was there. So because it's not dissipating the energy, it won't draw as much, but anything plugged in does draw what's called, anybody know the electrical term for that? I don't know what it's called, but when you have something plugged in and it's always drawing energy, anything plugged in always draws energy, unless you have a power surge attached to it. Power surges are made to cut the circuit. But if you have like a lamp plugged in or a laptop, even though it's not currently charging, if the laptop's off, it still draws. There's a term for that. It's like leakage in a sense. It's the energy literally leaking out of the outlet into your appliance. There's a term for it. I don't know, whatever. But yes, you do. You still do use a little bit of energy. Not nearly as much.
Do you have to use that formula though? That's something different.
What did you do in the end though? Tell me, in words, go ahead.
What I did was I got the 0.12 kilowatts.
Got it.
And I got 0.416.
Got it.
And I got 0.86 kilowatt hours. So I just set up a proportion. I did 0.086 over 1.
0.086 over 1. Why did you do a proportion? Why did you do it over 1 out of curiosity? It works still.
I got the same answer.
You do. You're always going to get the same answer because you're going to end up cross-multiplying to solve, right? And when you do that, your PT, what did you get for P times T? When you did 0.120 times 0.416, what did that become again? Yeah, that's going here, and then aren't you, by cross multiplying, aren't you multiplying by 0.086? So inherently you're doing that. And this is on the formula sheet, so if you want to just use this or do what you did, it's honestly fine, either way. What you're doing is really just dimensional analysis by setting up a proportion. You're seeing that these units are canceling or multiplying. It's fine, Jim. Yep. Problem sets, yeah. No, that was yours actually, wasn't that?
Yeah.
He's up next. Oh no, you had the same question? Alright, so unless somebody else has one before 10, you already asked one. No other problem set questions? It's all yours, yeah.
Number 102.
102? Number 10 says the following. A 94 ohm resistor is connected to a 15 volt battery. How much energy is dissipated in the by the resistor in 6 minutes? So we're just doing power times time, the first half of that last formula. So remember the last formula, it was cost equals energy times rate. Well, now all you're looking for is the energy. That's what this problem is asking for. So remember earlier, we just said power is energy over time. So power times time will give you energy. So this is what you need for this problem. So in the problem they're giving for 102, the resistance is 94 ohms. The voltage is 15 volts. If you're given these two values, for me, I would use power equals V squared over R for a problem like this. 15 squared over 94 will give me some number for the power. 2.4, thank you. That worked? No, it works. 2.39. 2.4 watts. And then I'm going to take that and multiply it by the amount of time to give me the amount of energy dissipated. Now, it's really a question of what are your units going to be for your energy. Units are usually given in kilowatt hours for energy. So you really should convert this. But theoretically, if you just take this answer and plug it in, take this answer and plug it in here, and you were given a time of what looks like 6 minutes. 6 minutes is a tenth of an hour, or you could simply just put 6 minutes in there, and your answer would be in watt minutes, which is units of energy, actually. So it's the units that would be the trickiest part here. So if I take this amount of power times this amount of time, just multiply them, my units would be watt minutes, right? Which is like kilowatt hours, just different units. So I could also convert this to kilowatts and then convert the other one to hours. All right, in another world or another part of this problem, if I wanted to, I could simply say, well, you know what, my time is simply a tenth of an hour, because that's where that comes from, 6 minutes. And my power would be 0.0024 kilowatts. So in essence, if I multiply these, it'd be 0.00024 kilowatt hours. That's how much energy would be used. So it's the same thing as really just doing what we set up here, 6 times 2.4, and those units instead would be in watt minutes. And although it looks weird, right, whatever this turns out, let's see, 6 times 2 is 12, 6 times 0.4 is 2.4, 14.4, and that would be in watt minutes. Those answers are identical. I could use this answer in watt minutes, or the converted time and the converted power from these two numbers converting down here and get kilowatt hours. It's 6 1/2 dozen. Okay, it's just change of units.
I had a question on 62.
62.
Set page 775.
Yes. Pacemakers designed for long-term use commonly employ a lithium iodine battery capable of supplying 1,500 coulombs of charge. What is that variable? You're not going to have to do math like this on the test probably. But just to give you a quick, it's 1,500 coulombs of charge. That's your delta Q. Okay? It says if the average current produced is 5.6 microamps, micro means times 10 to the negative 6. If that's the case, how long will what's the expected lifetime? Find T. So I would use this formula from the very beginning. Solve for T. And you have those two values. Delta Q is 1,500. That goes in here in the numerator. And the denominator is 5.6 times 10 to the negative 6. Okay, that's a negative 6 over here. It's 5.6 times 10 to the negative 6. So you literally plug in the numbers from a bit. But this is one, Ernest, that I'd rather you understand theoretically than mathematically. That the amount of current flowing through a wire is really the charge over the time period. But it's interesting to know. I mean, what did you end up getting? I'm curious. What does this become?
Well, I will go in. Is that in?
Yeah, because it's going to be, the units are going to end up being in seconds,
Yeah,
right?
I got like 2.678571429 e to -4 seconds.
Well, it can't be -4. It's got to be positive because you're dividing by a negative exponent right now. Try it again. Try 1500 over 5.6 times 10 to the -6.
2678574 2.9.
Can you give me how many in exponential? 2.6 times 10 to the... I guess like 8, 9? And this is in seconds. So divide that by 6, divide that by 3600. That'll tell us how many hours a pacemaker will last.
71.
Divide that by 24. Give us days, because it's so big of a number. 3,100 days. That's how long a pace. Divide that by 365. About 10, 9 years?
8.
Boom, there you go. So when you got a pacemaker put in for your heart, it lasts about 8 years, according to this math. Assuming Matej just did everything right, by the way.
Would you have to write it in seconds though, or seconds is the standard?
Yeah, so I gave the answer in seconds, and I left it that way. But I want you guys physically to understand the idea of this problem is that you're calculating the time of pacemaker. What happens if a pacemaker stops working, guys?
You die.
So is it really important that it lasts like 8 years? And how long do you think they check it after?
Every year, I assume.
I don't know. Anyone have a parent that has or a grandparent that has a pacemaker? If so, ask them. They probably go in for like a yearly check, and they probably replace it every 5 years. I mean, I don't think they'd wait till 8 years. Like, all right, it's gonna die in a month, so you better get in here next month, or you're dead. Hey, come on in. It wouldn't make sense, right? In 5 years, they're gonna say, hey, let's replace this thing. What is that called in engineering? It's called the factor of safety. Okay, when you replace something earlier than you have to do it, it's because of the factor of safety you're including.
Like it came with a name, but I don't understand. Like it came with like 2.6, but.
Because your denominator needs to be in parentheses, or either that, or you have to use scientific notation.
Okay.
So I would do 1500 divided by, and I would do 5.6 second EE -6, like that. And it
Okay.
automatically applies in the denominator.
Got it.
Okay? Or the denominator just goes in parentheses, because you have a multiplication in that denominator, right?
Yeah.
That operation has to occur first, and then the numerator has to be divided by that. So you need parentheses around your denominator to
Okay.
show that happens first. That EE command, though, makes it happen first, so you don't have to worry about it then. Other problem set questions. So just to reiterate, formula-wise, right? So we really went over every formula by doing these questions. Those are great questions because those encompass like everything that we have to think about. Theoretically, we talked about a lot of stuff. We talked about variable resistors called potentiometers, like a dimmer on a light bulb. We talked about a generator versus a battery. A battery takes chemical energy and you get electrical energy. Yet a generator takes mechanical input and it gets electrical energy out of it. We also talked about the idea of resistance being affected by 4 things. 4 things affect resistance that we talked about. The cross-sectional area, meaning the bigger the wire, the more flow can flow. So bigger wire, less resistance. The length of the wire, the longer the wire, the more resistance because there's more collisions. The temperature, the higher temperature in the wire, the higher resistance felt by the wire. And then the material property. There was a video I sent out yesterday that was, it was kind of long, I guess like 15 minutes or so, I think. And it was talking about the history of electricity and how we're using AC circuits over DC and how electricity is delivered to your home and transformers. They also talked about material properties in that video. And they talked for a quick minute about the idea of why do we use copper? Because gold and silver and aluminum and copper, they all have pretty similar resistances. Why do we use copper? What's the reason, Ryan?
I see that we have an abundance of
There it is. Abundance of one material makes it cheaper. We use copper because it is cheaper than gold or silver or one of those. Now, they would pretty much work at the same value though. Okay, you get a little bit better conductivity out of gold, a little bit less resistance, but it really doesn't matter. It's negligible. It's not worth the cost. Yes?
Sorry, so width, then temperature, material.
And length. Longer the wire, the more resistance. Because think about it. Here, you have a wire that's this long, and you have a wire that's this long. Well, those electrons, they have a lot more collisions when the wire is longer, right? So these electrons are getting slowed down before they get back to the battery. And then they get back to the battery. Versus here, look at this. They get back to the battery much quicker, right? Less resistance, higher current. Okay, it's flowing faster. Those are the 4 factors that affect resistance. Yes?
So on this test, it's probably just going to be like more math, right?
No, it'll be pretty equal, the usual.
Okay.
Yeah, I'd say about it's going to be 40 or 45 points. I haven't finished it yet. I'd say probably 8 multiple choice. This is like 16, about a third, like 16 out of 45. Short answers usually about 12 points, and then math might be like 15 points. So about a third, usually about the same.
For multiple choice, which sections do you suggest we study?
They're all pulling out of there. I mean, the first two for sure more than anything. 21.1 and 21.2. 21.3 is highly mathematical. Okay? If you want to hear more about theory, guys, honestly, and like theoretical stuff, this was a good math review. In the other class, I did a highly theoretical review. I didn't really do much math at all. I went over all the topics. So watch the video from the other section, and the same thing goes, tell the other guys in the other section if they want to see some math problems to look at this video. Okay?